push a cup with a steady force, and the work done is 1 multiplication, force times distance, stretch a spring and that recipe collapses because the force changes at every point of the pull. This video builds the tool that handles any force varying with position, work as the area under the force versus position curve, and then proves the payoff, the work-kinetic energy theorem. The work done on a body equals its change in kinetic energy, exactly. Final speeds will fall out of a single integral with no equations of motion in sight. A body moves along the x-axis from an initial position, x sub I, to a final position, x sub f, pushed by a force whose x component depends on position. Graph that component against position, and a sample force might trace a bell-shaped curve, small near the start, peaking in the middle, small again near the end. For a constant force, work was the force component times the displacement. But this force is not one number. It is a different number at every point. Multiply the displacement by the peak value, and you overestimate the work. Use the starting value, and you underestimate it. No single choice is right. The escape is the central move of calculus. Over the whole trip, the force varies a lot, but over a short enough piece of the trip, it barely varies at all. So chop the trip into pieces. Divide the displacement from x sub I to x sub f into a large number n of small pieces, and look at a typical piece. Call it piece j, with width delta x sub j. Over one narrow piece, the force barely changes, so replace it by its average value on that interval. The work done on piece j is that average force times the width. On the graph, the area of a thin rectangle sitting under the curve. Work is a scalar, so the total work is the sum of all n rectangle areas. But that sum still depends on how we chopped, on the number of pieces and on their widths. To get a quantity independent of the chopping, take the limit as n goes to infinity while every width shrinks to 0, both conditions together. In that limit, the staircase of rectangles hugs the curve exactly, and the sum becomes the definite integral of the force component with respect to position. W equals the integral from s sub I to s sub f of L sub x of x dx. Geometrically, the work done by a varying force is the area under the force versus position curve between the endpoints. Keep that picture. Every result that follows is an area. Now the classic varying force, a spring. An object rests on a smooth, frictionless table, attached to a spring whose other end is fixed to a wall. The spring has spring constant k. Place the origin at the object's position when the spring is relaxed, with positive x pointing in the direction of stretch. Stretch the spring by an amount x sub I and release the object. The question, how much work does the spring do on the object by the time the stretch is x sub f? By Hooke's law, the x component of the spring force is F sub x equals negative kx, proportional to the stretch, always pointing back towards the origin. Graphed against x, that is a straight line through the origin with negative slope. Mark x sub f and x sub I on the positive axis. The work is the signed area between the line and the axis, from x sub I to x sub f. The integral does the bookkeeping. W equals the integral from x sub I to x sub f of negative kx dx. The antiderivative of negative kx is negative 1/2 kx squared. Evaluate at the endpoints. W equals negative 1/2 k times the quantity x sub f squared minus x sub I squared. Both endpoints enter as squares, so the sign of the work does not depend on the signs of x sub I and x sub f, stretched or compressed. Only the magnitudes matter. If the spring ends up less stretched or less compressed than it began, the magnitude of x sub f below the magnitude of x sub I, then x sub f squared minus x sub I squared is negative. The leading minus flips it, and the work is positive. In words, The spring force does positive work whenever the spring moves from greater tension to lesser tension. That is exactly our released object. The spring relaxes as the object moves. The pull lines up with the motion, and the spring pours energy into it. Stretch the spring further instead, and the spring fights the motion, and its work is negative. Work shares its unit with kinetic energy. Both are measured in joules. That is not a coincidence. It is a theorem. Start from the definition of work and bring in Newton's second law. For a point-like object, f sub x equals m times a sub x. So w equals the integral from x sub I to x sub f of m a sub x dx. Now rewrite the integrand. Acceleration is the rate of change of velocity dv sub x over dt. And in a time dt, the position changes by dx equals v sub x dt. Combine the two, and the combination a sub x times dx equals v sub x times dv sub x. The position integral becomes a velocity integral. W equals the integral from v sub xi to v sub xf of mv sub x dv sub x. That integral is elementary 1/2 mv sub f squared minus 1/2 mv sub I squared. The right side is the final kinetic energy minus the initial kinetic energy. So W equals K sub F minus K sub I, which is delta K. This is the work-kinetic energy theorem. It is exact, an identity that follows from Newton's second law and the definition of work, valid whether the force is constant or varying. One caution, the W in this statement is the work done by the total force. Every force acting on the object, summed before you integrate. The theorem reads sign by sign, positive total work, kinetic energy rises and the body speeds up. Negative total work, kinetic energy drains and the body slows down. Zero total work, kinetic energy, and therefore speed, stays constant. Notice the word speed. Kinetic energy has no direction, so zero work does not promise constant velocity. A force held perpendicular to the motion does no work and never changes the speed, yet it can bend the direction of travel. Gravity on a falling ball does positive work. Faster, gravity on a rising ball does negative work, slower. Friction on a sliding cup does negative work, slower. Every force in the problem casts its vote through one signed number. Put the theorem to work. A ball of mass 0.2 kilograms starts from rest at 15 meters above the ground and falls to 5 meters above the ground. Find the change in its kinetic energy, and from it, the ball's speed at a lower height. Measure y upward from the surface. The initial height is 15 meters. The final height, 5 meters. During the fall, gravity is the only force acting, so the change in kinetic energy equals the work done by gravity. For a constant gravitational force, that work is negative mg times the change in height, negative mg times y sub f minus y sub 0. Substitute the numbers, minus 0.2 kilograms times 9.8 meters per second squared times 5 meters minus 15 meters. The height change is negative 10 meters. The two minus signs cancel. The work is positive 19.6 joules, about 20 joules to two significant figures. The sign checks out physically. Gravity points down, the ball moves down, so gravity feeds the ball energy. Now invoke the theorem. Starting from rest, the initial kinetic energy is 0, so delta K is 1/2 mv sub f squared, and that equals the work. Solve for the speed. V sub f equals the square root of 2 times the work over the mass. 2 times 19.6 joules is 39.2. Divided by 0.2 kilograms gives 196 meters squared per second squared. The square root is exactly 14 meters per second. And the theorem prices the return trip too. A ball rising from 5 meters back to 15 meters receives negative 19.6 joules from gravity, shedding exactly that much kinetic energy on the way up. One more example, this time with two forces doing work at once. A person pushes a cup of mass 0.2 kilograms along a horizontal table. The push has magnitude 2.0 newtons aimed at 30 degrees above the horizontal, and it acts over a distance of 0.5 meters. The coefficient of kinetic friction between cup and table is 0.1. The cup starts at rest. Find its final kinetic energy and final speed. The theorem uses the total work, so audit every force. Gravity and the normal force are perpendicular to the motion. Zero work from each. The push and the friction remain. The horizontal component of the push is 2.0 newtons times the cosine of 30 degrees, 1.732 newtons. Friction takes more care because the tilted push changes the normal force. Vertically, the cup does not accelerate, so the normal force plus the upward component of the push balances the weight. The upward component is 2.0 newtons times the sine of 30 degrees, exactly 1.0 newtons. The weight is mg, 1.96 newtons. So the normal force is 1.96 minus 1.0, 0.96 newtons, noticeably less than the weight. The friction force is mu sub k times the normal force, 0.096 newtons, pointing backward. Now total the work. W equals the horizontal push component minus the friction force, all times the displacement. 1.732 newtons minus 0.096 newtons is 1.636 newtons, times 0.5 meters gives 0.818 joules of total work. Since the cup started from rest, the theorem says that number is the final kinetic energy. K sub F equals 0.818 joules, 0.82 to two significant figures. The speed follows. V sub F equals the square root of 2K sub F over m, the square root of 8.18 meters squared per second squared, about 2.9 meters per second. One habit worth copying: carry unrounded values through and round once at the end. Round the work to 0.8 joules too early, and the speed comes back 2.8 instead of 2.9. Step back and see what the theorem buys. The old route to a final speed runs through the equations of motion. Find the acceleration at every instant, integrate over time for the velocity function, then evaluate it. The new route computes one number, the work, the area under the force versus position curve, and that number is the change in kinetic energy, exactly. The falling ball, 19.6 joules of gravitational work, and the speed at the bottom follows. The pushed cup, 0.8 of a joule of total work. Push credited, friction debited, and the speed follows again. Constant force or varying force. The recipe is the same. Identify the forces, integrate over position, read off delta K. One curve, one area, one answer. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.